Hello everyone and welcome to Control Engineering and Control Theory tutorials. In these tutorials we present real and applicable knowledge of control engineering, signal processing, machine learning, optimization, and applied mathematics. In this particular tutorial we explain how to implement a linear quadratic regulator or LQR controller in Python. This video tutorial is based on the Python Control Systems library. This library is a very powerful tool for simulating dynamical systems as well as control design. You can, for example, compute step responses, you can design PID controllers, you can design H2 or LQR controllers by using this library. An attractive feature of this library is that it's completely free, in contrast to MATLAB. For example, for a commercial MATLAB license, you need to pay thousands of dollars. And many small companies and private researchers cannot afford to buy the MATLAB license. And consequently, you need to search for an alternative. And a good alternative is this library. Before I start with detailed explanations, I will first briefly summarize the main topics that will be covered in this video tutorial. We will start with a simple mass spring damper system, and this is our test case for testing the LQR controller. Then we will derive the state space model of such a system, and finally I will explain how to design an LQR controller for such a system. After briefly covering the theory of LQR control, I will explain the Python code that you can see over here. If I run this Python code, I will see these graphs. These graphs show the step response of our LQR controller. And by the end of this video, you will learn how to generate these beautiful graphs. But before I start, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as almost 300 video tutorials that you can find on my YouTube page. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. To explain the basic principles and ideas of the LQR algorithm, we use an example of a mass spring damper system that's shown over here. We have a point mass that is driven by the force F. The force F is the control force, and we want to compute this control force such that the mass is moved to a certain position, for example over here, and such that the mass is stabilized. Mass is attached to the wall by using a damper and a spring. Next, let us derive a state space model of this system. By introducing the state space variables x1 is x, and x is the distance from the equilibrium point, and by introducing x2 as x dot, and x dot is the velocity, we obtain this state space model on the basis of Newton's law. If you want to know more how to derive the state space model, you can click over here, and this link will lead you to a detailed tutorial that I created and that explains how to derive the state space model. In this state space model, Ks is the spring constant, Kd is the damper constant, m is the mass, and F is the external force that's being applied to the point mass. F will be denoted by U, and U is our control input that we want to determine. We can compactly write this equation in the standard form. X dot is Ax plus Bu. Next, let's form the output equation. We assume that we have a sensor that measures the distance from the equilibrium point x, and consequently our output equation will have this form. The goal of the set point regulation is to steer the system to the desired state or desired state set point, and we denote this state by xd. And we start from some non-zero initial state that in the general case is different from xd, and we assume that the disturbances are acting on the system. Again, the control objective is to drive this mass to the certain final state. under the presence of disturbances and external effects. That is, we need to find this force F that will be a function of x and x dot such that the mass is stabilized. In this tutorial, we assume that the full state information is available at every time instant. That is, we assume that both x1 and x2 are available. Everything presented in this lecture can be generalized for the case in which only the position x1 is available. In this video lecture, we will use the terms desired state and desired set point interchangeably. The first step is to determine the control input UD that will produce the desired state XD in the steady state. Here XD is a constant steady state that's determined by the user. Since XD is constant, its first derivative is 0, and by substituting XD instead of X in this equation, we obtain the equation number 4. We want to solve this equation for UD. That is, for the given XD, we want to determine UD. Over here, we assume that the desired state, XD, is physically feasible. So what is a physically feasible state? For that purpose, let us consider our original graph. Let us assume that we want to drive this mass to the following state. XD is equal to, position is equal to 3 meters or centimeters or millimeters. It's completely irrelevant, and the velocity is 0. And we want to keep the system at this state. This is obviously a feasible state. That is, a feasible steady state. We can obviously determine this force F, a constant force F, that will drive the system to this state. However, let us assume that someone selects this desired state, 3, 1. We want to drive the system in steady state to the position 3, and we want the steady state velocity to be 1. Is this physically feasible? Obviously, the state is not physically feasible. That is, it's not physically feasible steady state simply because if the position that's equal to 3 is steady state, this means that we stay at that position, and consequently the velocity needs to be 0. So when selecting the desired state, it's very important to keep this physical constraint and to keep in mind this physical constraint. Under the assumption that XD is a feasible steady state, and under the assumption that the matrix B has a full column rank, we can solve this equation for UD, and the solution is given by the equation number 5. In principle, we can control the system by applying the constant control input UD and by waiting for the system to settle down in the desired steady state. And as the result, you will obtain a graph that looks like this. Okay, so the system over here goes to the desired state of 2 after, for example, 15 seconds. And here's the velocity. The velocity naturally goes to 0. However, is this a good steady state response? The answer is no. You should never design a feedback control system to behave like this. This system is not very well damped, and in addition, since you have nonlinearities in the system, these oscillations might explode. To summarize, although we can, in theory, determine constant UD that will drive our system to XD in steady state, we practically rarely do that. The first reason is these oscillations, and the second reason is that we always have disturbances acting on our system. That is, besides inputs that you can see over here, we also have another term, d here, that affects our dynamics, and consequently, we cannot control the system exactly like this. However, this computed UD is very useful for designing our controller. To develop the control algorithm, we need to introduce the error variables. X tilde is simply a difference between our current state and the desired state, and consequently, we obtain that X is X tilde is an error, plus XD. Similarly, we introduce control input errors, U tilde. U tilde is simply the difference between the absolute control minus UD computed by using this equation. And consequently, we can express U from this equation. Now, let us differentiate these expressions and let's substitute the equation number 6 in the equation number 2. Let's see the result. As the result, we obtain this equation. And this equation is very important. Here, it should be kept in mind that since xd is constant, we have that the first derivative of xd is 0. By substituting this fact in this equation 7, we obtain the equation number 8. And notice what happened over here. This is a very important equation. We have expressed the first derivative of state error as a function of state error, control input error, and desired state as well as desired control input. On the other hand, let us substitute the equation number 4 in this equation. And what happens? These two terms simply die out. They're effectively equal to 0. And consequently, we have our error dynamics. Stop here and think about this equation. We are saying that the first derivative of the state error is simply A times state error plus B times input error. And we will design the LQR controller for this equation. The LQR algorithm optimizes the following cost function. The first term is the state error, the second term is the input error, and the third term is the cross-coupling. Here, Q, R, and N are the weighting matrices that are selected by the user. That is, by properly choosing Q, R, and N, we can tune our algorithm. As mentioned previously, the matrix Q penalizes the control error, and generally speaking, larger values of Q will increase the speed of the system response. However, the trade-off is that more control energy will be spent to steer the system to the zero state. On the other hand, the matrix R penalizes the control energy. Larger values of R will generally minimize the control energy, however, at the expense of reducing the system's response speed. So it's always a trade-off. And then we have this third term weighted by the matrix N that is basically a trade-off. In this video tutorial, we assume that the Q and R matrices are simple identity matrices that are scaled, where Q and R are scalars. The solution of the LQR minimization problem is the feedback control algorithm given by the equation 12. Here, the matrix K is the feedback matrix determined by this equation. And we can see over here that this is a state feedback control law. In this equation, the matrix S is the solution of the algebraic matrix Riccati equation. And here is the Riccati equation. Fortunately, you don't need to solve this equation directly in Python. The Python control systems library has a nice function that I will explain later that solves this equation for you automatically. So you don't need to worry about it. Don't be scared of the Riccati equations. Let us now substitute this equation 12 in equation number 9, and let's see what happens. As the result, we obtain the equation number 15. The LQR control algorithm will make the matrix A minus BK to be asymptotically stable. This means that all the eigenvalues of A minus B times K are in the left half of the complex plane. This means that the set point state error will asymptotically approach to zero. That is, the LQR control algorithm will make this error to approach to zero. What does this physically mean? Let's go back and analyze the definition of x tilde. X tilde is equal to x minus xd. Since x tilde will go to zero asymptotically, that is infinity, x will approach xd in infinity, and we will achieve our control objective, since the control objective is to drive x to xd. This is very important to keep in mind. Let us now substitute x tilde in this equation. As the result, we obtain the equation number 16. That is x dot, and remember that x is the absolute state, is equal to A minus BK times x, and this matrix is asymptotically stable, minus A minus BK times xd. Here is our xd that serves as the reference state. This equation is very important since it will be used to simulate a closed-loop system in our Python code. Next, let us analyze this equation over here. By substituting the values for u tilde and x tilde in this equation, we obtain the equation number 17. And the equation 17 is very important if you want to implement this control algorithm in hardware. This equation tells you that input u that you will send to your actuator or that you will drive your system with, for example, in our case u is the force, is equal to the desired force determined on the basis of the desired state by solving this equation, and this desired force is constant minus this term over here. X is the measured state. That's very important to keep in mind. Over here we assume that x can be completely measured, and xd is a known desired point that's set by the user. And this whole algorithm is a state feedback algorithm. Okay, let's start with Python coding. The first step is to install the Python control systems library, and to do that I will be using Anaconda Navigator. I will click on environments, and over here I will click on base on root, click over here and open the terminal. Then I will simply type pip install control. The name of the library is control. And as you can see over here, the requirement is already satisfied. This is because I have already installed this library. In your case, you will see installation progress. Close this window and start your favorite Python editor. In my case, I'm using Spider, so consequently click over here. And after some time, your Spider Python environment will open. I like Spider very much since it reminds me of MATLAB. You can simply select certain piece of code, you can do the right click, and you can simply execute this selection. This is very convenient. Furthermore, over here you can type whos, and if you know MATLAB very well, MATLAB has a command that's called whos, and it's very similar to Python command. By using this command, you can see all the variables in your workspace. First, let's clear our environment. Let's erase everything. And let's type CLS. Perfect. The first step is to import the necessary libraries. First we import the plotting library, then we import our control systems toolbox as CT. And this is the standard convention for importing this toolbox. And finally we import NumPy. Next, over here I created a simple plotting function that will be used to plot the graphs. This function accepts x-axis vector that will correspond to time vector, y-axis vector that will correspond, for example, to first state or to second state. Here's the title of the graph. This is the string that's a label on our x-axis. This is a string that is the label on the y-axis. And this is the file name for saving our graph. And here's how the function looks like. It's pretty much a standard plotting function. Nice thing about this function is that it will produce this file over here, and you can choose the resolution of the file. Usually I select 600 dots per inch. Let's start with system modeling. We need to define the system matrices A, B, and C, as well as D, and the initial condition. Here's how we do that in Python. First, let's define our mass, for example 10 kilogram, spring constant 100, damping constant 5. Here I deliberately selected a system that is not well damped, since I want to make the control problem as challenging as possible. Over here we define our system matrices by using NumPy arrays. Here's our A matrix. We can double check our A matrix. Here it is. And here's how you define the A matrix. Similarly, you define B matrix, C matrix, C matrix, and D matrix is 0. Next, let's define our state space model. Our state space model is defined by using this function SS. And to remind you, CT is our control systems library, since we import control as CT. So ct.ss defines our state space model. Over here, I will define our initial condition for simulation, and finally, I will print our state space model. Let's see the output. Here it is. Here's our state space model. Let's analyze the output. We have one input, one output, and we have two states. And here are the system matrices. Next, let's simulate the open loop step response of this system. Physically, this means that I'm applying a constant force equal, for example, to 1 Newton to this system. And I want to see the response of the system. To do that, we first need to define the start time. We start from 0 simulation. The end time of the simulation is 20 seconds. You can change these parameters, and assume that I have 500 samples between 0 and 20. Next, I define my time vector over here. Perfect. Now I have my time vector. Over here, we need to define the control input vector for simulation. I'm simply assuming a vector of 1, since I want to compute the standard step response. Okay, and over here, I'm simulating the response of my system. The first argument is our state space model. The second argument is the time vector. The third argument is our defined control input, and the fourth argument is the initial state. Let's simulate the system and let's see the output. Okay, no output. So what's happening over here? Well, you can see that this function forced response actually produces this structure. So we need to decompose this structure. This structure is basically time response data object consisting of the following values. We can access the simulation time by typing return simulation.time. So let's see our time vector. Perfect, here it is. Then we can access our outputs by simply typing return simulation.outputs. It's a very interesting data structure. Here it is. How about states? Here are the states. Okay, perfect. There are two states, and consequently this is a fat matrix with 2 rows. And here's the input used for simulation. Perfect. All ones, as we expected. Let's plot our output. To plot the output, we first call this function plotting function that we defined over here. And we specify the parameters. We need time as the first parameter. Then, what do we want to plot? Let's plot the first state in time. Consequently, we type return simulation.states and we select the first row. And over here, I simply provide the name to my labels and the title of my graph. So let's see what happens over here. Voila! This is how the position of our mass behaves over time when we apply a constant force of 1 Newton. We can see that the system is not very well damped. In practice, our response will look like this. If I apply a constant force F, this mass will go to a certain position. For example, I'll try to simulate that. It will go, it will go, it will go, and then it will oscillate over here, and finally after maybe 15 or 20 seconds the oscillation will be damped. However, we cannot wait for 15 or 20 seconds. We need a much faster and much more stable response. But before we design the controller that will enable us this response, let's see what happens with velocity over time. To plot the velocity, I simply select the second state, and here it is. We can see again oscillations, and after some time the velocity goes to 0, which means our system becomes stable. Now let's go back to our summary. This is our system and we computed the open loop step response. However, we first need to determine our UD. UD is the desired steady state input that will drive the system to desired state. To compute this input, we first need to specify what is our desired state. What is our desired objective? Over here, the desired objective is to move the mass to the point 2, where 2 can be 2 meters, and we want to have velocity of 0. Let's see what happened over here. If I apply the step response to my system, I can see that my system only moves for 0.01. However, I need my system to go to 2. Consequently, I need to find UD by solving this equation. And this is how we solve the equation in Python. We first define this matrix, and this matrix is a pseudo-inverse of B. That is this part over here. And after I do that, I need to multiply the result with A. So let's summarize this. This is the first step, and this part, let me just see over here, is matrix M1. The matrix M2 is this product. M2 is simply M1 times A. And that's exactly what is written over here. And finally, UD is simply M2 times XD. That is, we solve this equation to compute UD. And here is our UD. So let's see UD. Here is UD. It has a large value of 200. So we need 200 newtons to move the mass to 2 meters, for example. Next, let us simulate what happens when we apply this constant input or force to our system. Again, to do this simulation, we need to define the time vector and we need to define the control input vector. Okay, let's do that. Here I have to be more careful. Okay, this is our control input. Here it is, 200 everywhere. And again, we need to call this function forced response. We specify the system, time vector, input vector, and initial state. Perfect. And again, we will pass this data structure with appropriate time and states to our plotting function, and let's see the response. Voila, here is the response. We can clearly observe that our desired input, that is the desired steady state input, will drive our system to desired state 2 in the steady state and for velocity 0. However, the issue over here that we have very undamped system, and we don't want that. You should never design a control system that acts like this. you need to dampen these oscillations and you need to have a faster rise time, or better to say faster settling time. Let's design our LQR controller. The first step is to select the weighting matrices Q and R. Going back to our summary, we need to select Q, R, and N. Here, I assume for simplicity and in order to make this video tutorial as short as possible, then N is equal to 0. Consequently, I only need to select Q and R. I select large value of Q since I want to put emphasis on stabilizing my system and on the speed of the response, and I select R is equal to 1 since I don't care about the energy. I assume that I'm very rich, I have enough fuel, and R is a small value. Okay, to compute our gain matrix K, that is, this feedback control matrix K, we need to use this function, LQR. The first argument is our system, the second argument is Q matrix, and the third argument is the R matrix. Of course, if you have N, you will include N over here. So let's do that. And you can basically see that in a fraction of a second, the function LQR returns the results. The results are the following one. K is the gain matrix, S is the solution of the Riccati equation. Here's our complicated Riccati equation, and this function gives you the solution of this equation, and the final vector, E, is the vector of eigenvalues of the closed loop system. That is, the eigenvalues of this matrix. So let's see the results, and let's analyze the result. Here's my E matrix. Let's start with the E matrix. Here are the closed loop poles. Not bad, not bad. However, we will see the response in a second. Let's see our Riccati equation solution. Here it is. Symmetric matrix, positive definite most likely. That's good. And let's see our gain matrix K. Perfect. It's a row vector as expected since K is multiplying state. Okay, let's now simulate this closed loop system. To simulate the closed loop system, we will be using this equation. We simply decomposed our aerodynamics in absolute coordinates. And now over here, xd serves as the constant input. This is very important. So we need to simulate such a system. To simulate such a system, we need to define our A minus bk. This will be our new A, and this will be our new B. Actually, minus A minus bk will be new B matrix. So I have a closed loop, and to make this video as clear as possible, this is our ACL. Okay, this is our BCL. Okay, and let me erase this. Let's go back to our code. Here's ACL, here's BCL, simply minus ACL. This is DCL. Okay, DCL should be 0, 0. And over here we define our new state space model. Let's do that. This state space model has the state equation that's precisely this equation. And then in order to simulate this closed loop state space model, we will simply specify our xd, but now as a matrix where one dimension of the matrix will correspond to time and another dimension of the matrix will correspond to actually desired state. Let me now summarize this in order not to confuse you. xd will look like this. As a matrix, I'll denote it like this. It will be xd, 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 until the end, xd. Where this axis over here corresponds to time samples for simulating our system. And this will be our new input for simulation. Okay, let's go back to our code and let's proceed. Again, we need to define the time vector and we need to define the input vector. And here's how we define the input vector. I explained this a second ago. I take xd 0, 0, xd 1, 0, and I multiply with vectors of 1s to obtain a fat matrix. Here it is. And then again, we need to use the function force response. We specify the name of our system, we specify time vector, we specify the input matrix, and we specify the initial state. Okay, here it is. And let's plot the results. Again, I'm using the function plotting function and specifying the corresponding time and state vectors. However, right now, the state vectors, and you can see it over here, correspond to the state of the closed loop system. And let's see the result. Here it is. You can see how we were able to stabilize our response. Remember the response that looked like this, right? We had the response that was going crazy. It was going like this. Okay? However, right now we have a relatively stable response. Perfect. Let's see the other variable. That is, let's see our velocity. Okay, not bad, not bad. The velocity is also stabilized. Let's see now what happens if we, for example, decrease our Q matrix. Let's see what happens. And let's repeat the complete simulation procedure. Here it is. We obtain a degraded response. This is because we decrease Q matrix. And by properly selecting Q and R matrices, you can actually tune your control algorithm. But don't forget the N matrix, because the N matrix will also give you an additional degree of freedom. Okay, that would be all for today. I hope that you liked this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.